We are going to find a power series representation for the function f of x is equal to 5 over 1 minus 4x squared and find the interval of convergence. Well, we have what I'm going to call a foundation function, which I'm thinking of now, and it is, we know how to express 1 over 1 minus x as the sum as n goes from 0 to infinity of x to the n. My goal then is to make f of x equals 5 over 1 minus 4x squared look as much like 1 over 1 minus x as I can, at least its structure. So I'm going to factor out the 5 just so it doesn't get in our way, pull it out, and now I have 5 times 1 minus, and really I just have 4x squared is the thing that would take the place of x. So our f of x, whoops, started writing in highlighter there. Our f of x is equal to 5 times the sum as n goes from 0 to infinity of 4x squared to the n, which I'm going to express as 5 times the sum as n goes from 0 to infinity of 4 to the n times x to the 2n. So there's our power series representation. As a geometric series, this will converge if the base of the expression, 4x squared, is less than 1 in magnitude. Since it's x squared, I'm not using an absolute value. But that would imply that x squared is less than 1/4, which would then imply that the absolute value of x is less than 1/2. So we get the interval of convergence as the open interval from -1/2 to 1/2. And we know it's the open interval because this is based on basically a geometric series. The next function we're going to represent is f of x is equal to 4 over 2x plus 3. Now this looks vastly different from our foundation function, which is 1 over 1 minus x. Oh, the ways it's different. First things first, I have a 1 minus x in the denominator for the foundation function. Here I have 2x plus 3. The order is backwards. We can deal with that. Second, the constant in our foundation function is 1, right? We have 1 over 1 minus x in the denominator. Here we have a 3, 2x plus 3. We can deal with that by dividing numerator and denominator by 3. Or as I write it, multiplying numerator and denominator by 1/3. By doing that and then playing that trick with the denominator of turning the sum into like a minus minus, we have f of x is equal to 4/3 divided by 1 minus the quantity of -2/3 x. I now have something that resembles the structure of our foundation function. So I know I can express this as the sum as n goes from 0 to infinity. And I got a little ahead of myself here, folks. I have a 4/3 in the numerator, and it would be easier for me if I just pull that 4/3 right out of the sum. The base is -2/3 x, and that's going to be to the n power. I can express that as 4/3 times the sum as n goes from 0 to infinity of -1 to the n times 2 to the n over 3 to the n, all times x to the n. Now that's a lot of stuff running around. You'll notice that I will not always, but often pull a negative factor out as a -1 to the n, but not always. Now I'm going to say we're not done with this one. The reason is, out front we have a 4/3. In the denominator inside the sigma notation, I have a 3 to the n. That's a common base. We can combine those. So I'm going to write this as the sum as n goes from 0 to infinity of -1 to the n. And in the denominator, I'm going to call that 3 to the n plus 1. Right? We're adding one factor of 3 to the common base that we had of 3n. I still need an x to the n, and now we need to deal with the 4. Well, folks, that 4 out front is the same thing as 2 squared. That's 2 factors of 2. I'm going to add those to the 2 to the n. So I have the sum as n goes from 0 to infinity of -1 to the n times 2 to the n plus 2 over 3 to the n plus 1, all times x to the n. That is our power series representation. As far as the interval of convergence, this will converge if the absolute value of our original base, -2/3 x, is less than 1. By solving for x, we will find that the interval of convergence is -3/2 to 3/2, and it's again an open interval. I'm going to ask you to work on the next one. It is f of x is equal to x over 2x squared plus 1. I'll get you started though. That x in the numerator, we're going to treat it just like we did the 5 and the 4/3. I'm going to call it x out front times 1 over, and that's as much as I'm going to help you. Well, no, I'll say one more thing. I am thinking, guess what, of a foundation function, and it is 1 over 1 minus x, which is represented as the sum as n goes from 0 to infinity of x to the n. I bet you were wondering how I was going to fit it into that bubble there. I couldn't. Anyway, go ahead and pause the video, come up with a power series representation and an interval of convergence to the best of your ability. Come back when you are done. I'm expressing 2x squared plus 1 in the denominator as 1 minus the quantity of negative 2x squared. So negative 2x squared is the base for our sigma notation. We have x times the sum as n goes from 0 to infinity of negative 2x squared to the n. I'm pulling the negative 2 to the n out as its own factor. I don't need to pull out the negative 1 and then also call it 2 as two separate factors. You can, but I just didn't feel like it. And then x to the 2n. And so we have x times the sum as n goes from 0 to infinity of negative 2 to the n times x to the 2n. And as you can see, we have a common base of x, one outside, one inside the sigma notation. I'll combine those and call it the sum as n goes from 0 to infinity of negative 2 to the n times x to the 2n plus 1. This will converge if the original base, negative 2x squared, in magnitude is less than 1. Solving for x, or the absolute value of x there, we get that the absolute value of x is less than 1 over the square root of 2. So the interval of convergence is the open interval from negative 1 over the square root of 2 to 1 over the square root of 2. And I'm boxing the two portions of the answer that we're asked for.